Okay, I hope that you can hear me. Please let me know. Can you hear me too? Okay, thank you. So today we are going to see a different use of the strain gauges, and we will see the usage of these strain gauges as a transducer. So not only for the strain measurement. Okay, one of the best application for the strain gauges is the load cell. So the use of the strain gauge as a load cell. Okay, so one idea is that, for example, we have a solid bar, let's say steel, aluminum, or whatever, okay, in a prismatic shape. So just the one that I'm going to draw here. Okay, like this. And then we apply an external load, for example, force, okay, like this. At two opposite faces of this solid bar. And moreover, we bond on this structure 4 strain gauges in this shape. We got R1 here. Then there. So we call it R1, R2. And then we will have R3 on the opposite side. Like this. So R3 and the other one is somewhere there. R4. Okay. So that if you look the structure from the top, if we define this reference frame, oh, okay. I'm waiting for the laptop to start recording the class. I don't know. Hmm. Okay.
Professor, sorry, I cannot hear you.
Yes, I'm waiting for the computer here in the classroom because it has some issues. Now it is restarting.
Oh, okay.
Just a few seconds.
Thank you.
I don't know what's happening. Can you see the screen at home?
Yes, Professor.
Okay.
Yes.
Okay, thank you. So I think that we can do here while waiting for him. I think that you can have one chair here. You have another one. Try to keep the safety distance. Okay, like this. I think that you can see that. You can take this other chair. Okay. So that we can manage to have our class until we wake up as soon as possible. So what we can do now when referring to a loss cell, we have this solid in this shape. We bond the 4 strain gauges characterized by a 1, 2, 3, and 4. And if you look at this strain gauge system from the top, for example, here, we have these different locations. Okay. Now, okay, because of that, we can think to connect these 4 strain gauges in a Wheatstone bridge like this one, okay, in which R1, 2, 3, and 4 are part of the 4 legs of the Wheatstone bridge. So what happens? It happens that because of the external force F that is acting on the solid here, okay, we have a strain that is sensed by the strain gauges, okay? And by the way, strain gauge R1 and strain gauge R3 are feeling the same strain, and whereas the R2 and R4 are feeling the same strain gauge, but of course it is the transverse strain with respect to the R1 and R3. Okay. Now, by the way, what is the expected strain that we are going to measure? We can write that the strain that I call epsilon A, that is the axial one, okay, could be related to the external force F divided the cross section of the test specimen, so A, let me call it AT as the test specimen cross section, that is this one, okay. So we got the stress here divided once again by the Young modulus of the strain of the test specimen, okay. And that is the axial one, so the strain that is fed by the R1 and R3 strain gauges. How about the transverse strain? We have to introduce the Poisson ratio, okay. So what we can say is that start if we can. The transverse strain is just negative Poisson ratio times the axial strain, okay. That is negative ni force divided the cross section of the test specimen times the Young modulus, okay. So what we can say is that let's put the things together in a Wheatstone bridge circuit. And so what we got, if you remember, we have the output tension relative to the input tension is equal to lower R, 1 plus R squared, and then the summation of the change in the resistances. That is delta R1 over R1 negative delta R2 over R2 plus delta R3 over R3 negative delta R4 over R4. Okay, now what we got here is that we are using the same strain gauge for all the 4 legs. We are using the same strain gauge. So R1 is equal to R2, that is equal to R3, that is equal to R4. That means that R is equal to 1. And of course, the balancing condition is met as well. Okay, so what we got is that this equation could be written as delta E star over B is equal to 1/4 the summation delta 1 over 1 negative R2 plus delta R3 over 3 negative delta R4 over R4. But now, delta R1 over R1, as I said before, is equal to delta R3 over R3, and is equal to the strain gauge factor times the axial strain. Remember, R1 and R3 are measuring in the direction of the axial force. Okay. But because we already defined the axial strain using this formula, we can put things together. So we can say is that is equal to kg, force, over the cross section times the Young. Delta R2 over R2 is equal to delta R4 over R4, that is equal to the strain gauge factor times the transverse strain. Okay, this one. So that is equal to negative kg Poisson ratio, and once again F over the transverse section times E. At the very end, the output tension with respect to the input tension is equal to kg force over twice AT Young modulus times 1 plus the Poisson ratio. Okay. Now, if we define a factor, let me call it Kf, the force factor of the load cell that we are going to measure, as this factor 1 over E divided by 2 ATE times kg, by definition, we will have that the output tension with respect to the input tension is equal to Kf times F. And that is a very nice formula, because what you got is a transducer that is capable to transduce the force into a change of a differential potential out of the Wheatstone bridge. Remember here. And the relation between the two is very nice. It's a linear one, just the fact that we have to know the Kf, so the load cell factor. Okay, and this load cell factor is just given you by the property, the material properties, in terms of the Young modulus, in terms of the Poisson ratio, the section, okay, the transverse section, and then your transducer in terms of strain gauge factor, kg. Okay, and that is very nice because, as I said before, it's a linear function, and it is a good approximation up to epsilon less than 1 per 1000. Okay, so it is a good one when we are referring to the typical strain gauge measurement, so that you can use the strain gauges also for the load cell, or also for the load measurement. Okay, and there are some of the shell available transducer like this one that you can buy.
Professor,
Yep.
what is that 1 hour? What is that, Professor? 1 hour 1000, strain less than or equal to
1000. Okay, it's not 1%, but 1000. So about 1, 2, 3,000 microstrains. Okay. So by using that, the value of the force, if K is equal to 2, is given you by this cross-section value Young modulus 1 plus the Poisson ratio delta E star over D. Okay, and this value of the force that could be measured is also telling me what are the limits of application of such a transducer. Okay, So, for example, let me check if we can measure a good value of force from the test material here, property from the resistance point of view. Okay, so let me see if this force is leading me to a critical condition for the material resistance when referring to the stress. Okay, so the stress, as you know, is given you by that equation, so the force over the cross section. And by taking into account that equation, what we got is that is equal to Young modulus over 1 plus me, and then the output tension relative to the input tension. And the strain, corresponding strain, is sigma over E, and that is 1 over 1 plus me, delta E star over. Now, let's discuss this. I will try to see if there are some limiting conditions in using such a transducer. Okay. Let's assume to consider, let's say, steel material. So E, the Young modulus is about 200 gigapar. The Poisson ratio is about 0.3. And then typical from the strain gauge measuring using the Wheatstone bridge is the typical change of output tension of about some percent, okay? Some per thousand, sorry, so 0.0, my calculations is 0.03. That is some per thousand. What we got for this is that the stress that we the stress that we can have is about 477 megapar. Okay, and the corresponding strain is about 2271 microstrain. Okay, so what we got is that for this condition we have no special remarks when referring to the stress, because the material is fully capable to withstand that kind of force, okay, that is generating me an output tension of this. Is typical. However, we are having constraint here because the strain corresponding to this operating condition is very, very large, more than 2000. Okay, so the limit in your operating condition are from the strain point of view instead of the stress point of view. The material is fully capable to withstand that kind of force, but the corresponding strain is too large. So we can have limits for the fatigue life, for example, if we are having cycling your forces. Okay.
Excuse me, Professor.
Yes.
I can't understand the letters inside the box.
What do you know? What is not fully understood from you?
That is written inside the boxes. The last two lines.
This one?
The bottom one, the bottom last.
This one?
Yes, the both.
Yeah, this is the corresponding stress, approximately, when you have an operating condition of about 0.003 delta output tension with respect to the input tension. That is one of the typical operating conditions, okay? We are also assuming that the material is made by steel, whatever alloy, and the corresponding Poisson ratio is 0.3. Under this operating condition, just by applying these two formulas, we can prove that the corresponding stress is about 400 and something megapascal, and the corresponding strain is 2000 and something microstrain. Are those information giving me some constraint in operating, some limiting condition for your strain gauges? The question is whether or not these values are very high or not. Okay. So
Yeah, thank you.
the answer to that is that we are not receiving any limiting condition when referring to the stress, because the stress is fully supported by the material. 400 megapascal is not that large stress. Okay. However, we are having full limitation when referring to the strain, because 2 and more thousand microstrain is a very large value. So we are having
Excuse me,
fatigue,
Professor.
fatigue problems will rule the applicability of your load cell based on the strain gauges. Okay? Questions?
Yes, Professor. I don't understand which K is equal to 2. K.
Which, sorry?
I remember that we had. Okay, there is written that K is equal to 2, but
No,
K.
yes.
K,
So-
not G.
I think K. Yeah.
K is equal to 2. See, typical strain gauges. Okay. K is the strain gauge factor.
Okay, so it is not KT or KG. It is a strain gauge factor.
Yeah.
Okay,
Yeah,
thank you.
yeah. Okay.
Thank you. Yes.
Let me see if I can.
And which material is this, Professor?
Steel.
The example that you wrote.
Steel.
Steel?
Steel.
Okay, thank you.
Okay, just one sec, please. I try to recap the class. Remember where it is. Here. I don't think it's my fault. I think that is some network issue. Okay, now having said that, how can you obtain such a operating condition? I mean, how can you be sure that your device is subjected to that force? What's happening in reality is that you must have sort of clamping device that is attached to your, let's say, test material. And then using this clamping device, you are applying the external force somehow, mechanical connection. Okay. So you need an external device, a clamping device. How sure you are that this external device is not introducing any bending moment, for example, just because it is not perfect, just because we are not in an ideal world, we are in a real world. So let's see what happens if, because of the clamping device, the axial force is not axial at all. Okay, so let's see what happens if there is what I call an eccentric load because of the external device, the clamping device that we need to apply. So effect of sectric loading. That could happen in reality. So what we got is, if we redraw the same picture as before, for example, you from the top, these are the reference frame, strain gauges to remember, R1, R2, R3, and R4. Okay, maybe on the other side, doesn't matter. Okay, and our load, instead of being just an axial load, so just a point load like this, it is sort of bending moment. Okay, double arrow means that there is a bending moment. And this is a representation of what could happen when we are dealing with an eccentric load. So we have an axial load whose amplitude is equal to F, as the one that we already considered. But because the action line of this 4 is not passing through the axis of this test specimen, it is somewhere, okay, then there will be that loading, axial load, plus the bending, that could be whatever. Okay, and this bending is M. Now we can take the composition of this bending into two main components with respect to the reference frame. So we got here what I call M1, and the other component is M2, component of the bending moment. Okay, so the effect of M1 is a bending, okay, the bending that is applied in the 2-3 direction, whereas M2 is a bending in the 1-3 direction. Okay, two different planes. So let's see what is the effect of both M1 and M2 in your measurement. So if there is M1, when considering just M1, the change of resistance of R2 relative change of resistance because of M1, so we are having a bending on a 2-3 axis, is equal to negative change of resistance on the fourth leg, R4. Okay, when again just M1 is applied. Also, what we got is that the change of resistance of, let's start with 1, of 1, the resistance 1, when applying only M1, is practically 0 compared to the R2 and 4, because they are almost in the neutral axis. So there is no strain measurement at all there. Also, that is practically the same when referring to delta 3/3 when M1 is applied. Okay. What happens when we are referring to M2? Same story. Okay. When applying it to M2, what we got is that the delta R1 over R1 when applied M2 is equal to negative delta R3 over R3. Okay, so let's refer to M2. M2 is this one. So 1 and 3 is having opposite strain. Okay, and delta R2 over R4 when M2 is applied is practically 0, as it is delta R4 over R4 when considering just M2. So at the very end, if you plug this information into your strain gauge equation, you can see from the very beginning, is it? Oh, yeah, that they compensate on each other. And thus, what we are saying is that there is no effect because of the eccentric load. So we are very happy this time because there is no noise in your measurement when referring to this load cell, okay, like this, because what is measured is just the amplitude of the force through the measurement of the change of the output tension when using force strain gauge in a Wheatstone bridge configuration like this one. Okay. I don't know if the class is being recorded now because of the fault.
You can still save the board though, right? Huh?
No,
Oh, you can't save the board?
I can see the board.
Okay,
yeah.
okay, okay. Yeah.
Until this turns on, I can't play it.
Mm.
It seems so because there is a red line over there.
Yeah.
I'm not sure. I really don't know. All right. So, okay, now let's see how we can use the same strain gauge measurement when referring, for example, to a pressure transducer using a very small plate. Okay, so the second transducer that we are going to see together, instead of a load cell, is a pressure transducer. So what we got here is that we have a shell like this, for example, with very small thickness, so the shell can vibrate somehow according to the vibration that we're going to measure. Okay, it could be because of the sound pressure vibration, because there is a change of pressure, whatever. Okay, somehow. So what we are doing is just applying sort of strain gauge over there. Now, we already consider the elastic property of a shell during the aerospace course. What we can say, and I'm reporting you to that, is that there is a radial strain as well as a circumferential strain. You remember, one in the radius direction of the shell, local radius, and then in the orthogonal direction. So what we can say is that the radial strain could be written as this way. I don't want you to remember this, but that is what we got. Okay. And the circumferential one is 3, 1 square, 8 ET square, but now what we're having is R 0 square, oh, delta V, in which ET Poisson ratio are the already well-known parameters. R0 is the external radius. Okay. The lower R is the radial position of the strain gauge that we are going to use. What is missing? T is the shell thickness. And finally, delta P is the change of pressure that is our unknown. Okay, so based on that, and by measuring these two strains, we can have an estimate of the change of pressure, so a relative change of pressure, so we can have the transduction of the pressure into some electrical quantity. Just to give you an idea of what's happening, we are having this very interesting plot in which I put in the x-axis the radial position of the strain gauge, lower R, and then the corresponding strain that is measured by your in the circumferential part. Okay, so what we got is something like that. Symmetrical should be. So here we got, oh sorry, R0, R0, and we have a maximum of circumferential one there when R is 0, and same for the radial strain here, epsilon R. Like that, should be, it's not very good choice. Okay, like that, more or less. So what we are having is the circumferential strain is always positive. Okay, the maximum circumferential strain is when R is equal to 0. Here. The strain in the radial direction could be other positive or negative. The maximum when R is equal to 0, as we already saw, but also when R is equal to R0, that is somewhere over there. Okay. Okay. So now we can use the strain gauge measuring setup that we already saw, the Wheatstone bridge. We put the strain gauge in one leg. Okay. So what we got is that we can prove that the output tension relative to the input one is given you by this equation. Here we go. Okay. In which R0 and Poisson ratio E and T are already defined. Alpha P is a constant that takes into account the measuring condition. and that is sort of coefficient 0.082. Okay, and that is your final equation. So you can relate the output tension that is measured by your strain gauge that is bonded on a shell of the shape. Here. Okay. The shell is reactive to the change of pressure, whatever is the source of that, I don't care about that. Because of that, there is a strain in a, let's say, if that is your R0, okay, then you have the circumferential one and the radial one. And then here is the final result of that. Just to put the things together. Okay.
Excuse me, Professor. I didn't understand that definition of alpha P.
Alpha P is just a number from the experimental point of view, and its value is 0.82.
And R. So you can you just scroll up a bit to show
Yeah.
me the surface? We had R0 and
Yeah, there is, because I showed you, there is here some parts that missing. So here is R. Okay, this is a plot in which I display the function of the strain as a function of lower R. Remember, over R is the radial position of the strain gauge. Okay, that could be, of course, a function of the distance. Okay, so if this position is equal to R0, then we got the maximum for the radial strain, where we got the minimum for the circumferential one. And when referring to the circumferential one, we got the maximum when lower R is 0. Okay, and then this is typical for that. However, the most important part is that when you link this to the strain gauge measurement setup, the Wheatstone bridge, then the output tension is sort of linear relation between your output tension and delta P. And that is good when you are referring to very small changes on the resistances, that is strain that are not that large as usually. And if the strain is not small, then the change of pressure is a non-linear function of the strain. Okay, that is, we are having distortion when you are measuring. Okay, and therefore we have to use other equations. I'm not going to.
and also I think because here we have only two surface, I think it is more reasonable to use half Wheatstone bridge. Am I right?
We are having just one strain gauge, so quarter bridge configuration.
Oh, okay, okay, okay. Thank you.
If you're having just one strain gauge, as I showed you before. But however, because the strain gauge is measuring both the, let's say, the natural and the transverse, that is the circumferential and the radial, then we have these two effects combined together. But however, you are right, because if you are using two strain gauges, then you have to use the half bridge configuration, and then you can measure both the circumferential and the radial strains separately, and therefore you can combine them in the Wheatstone bridge. However, the relation will be linear so far as the strain is not that large. Right? Okay.
And also, I have one more question. This is the only type that we can force a plate. I mean, we can even pull it or push it. I think.
Yeah, it is a change of pressure. Okay. So that could be positive or negative. Of course, the sign will depend on the change of the pressure, the sign of the pressure. Okay. However, the working principle is the same.
Thank you.
Okay. If you are measuring this, the change of pressure that is a dynamic property, that is the change of pressure is dependent on time, then we have that the natural frequency. So let me change the color. For dynamic measurements, that is the change of pressure is a function of time, not just a static one, then the operating condition is somehow limited by the natural frequency. So the natural frequency of the shell that we are going to see there should be larger than 1 order of magnitude of the characteristical frequency of your pressure variation in time. So should be larger than, let's say, 5, 10 times the frequency of interest, where f of interest represents the typical frequency content of your time dependent delta p. Okay. By the way, the natural frequency of the shell that is equal to 2 pi fm is equal to 1021 r0 square thickness, yes, and then GE over the coefficient. In which this gamma is the surface density, mass density. Okay, so it is kilogram over square meters. So with this very simple formula, you can also characterize what is the natural frequency of the shell, and therefore you can see whether or not you can use that transducer to measure your variation of pressure in time. If the typical frequency of the time domain pressure variation behavior is close to the natural frequency of the shell, then you can't use that one. Okay. If that frequency is much lower, 1 order of magnitude lower, then you can use this kind of transducer. Okay. Such a pressure transducer is very useful because it has limit cost. It is not that costly. Okay. Easy to use. Just a Wheatstone bridge. Okay. And the natural frequency is high. So you can have a number of frequency rate of pressure variation in terms of time dependencies. Okay. Questions on that? Okay. Let's have 5 minutes break. Okay, we have some breaks during the class already. 5 minutes. I'm trying to fix this problem. I can't even shut it off.
So is it because of the internet?
Hmm?
Is it because of the internet?
Don't know, maybe. maybe internet contributed to the overall slowness. Ah, I shut it off now. That's a good thing.
Professor, can I ask a question?
Sure.
I don't know if I understand it correctly or not. So as you said, if we have a transducer which has natural frequency near to the shell, it's better
No,
not
no,
to
no,
use.
no, not the transducer. I mean, the natural frequency of the shell is the one that is important. And I gave you the expression of the natural frequency. The transducer is having much higher natural frequency by itself. Okay. So the transducer is doing what the bonding structure is doing. So the natural frequency of the shell transducer system, strain gauge system, is the one of the shell. Okay. So that natural frequency should be higher, one order of magnitude higher than the typical frequency of your unknown pressure function, okay, function of time. That is what we are having.
Can you just repeat your last sentence?
The natural frequency of the shell strain gauge system
Yes.
should be higher than the typical frequency of interest of your pressure signal behavior, okay, of your signal.
Typical
Okay,
frequency
if you think of the pressure of the change of pressure as a function of time, this function on time could have, let's say, some frequency content, okay, that is ranging a certain frequency range, where this frequency content should be less than 1 order of magnitude with respect to the natural frequency of your system. Okay?
Okay, thank you.
Well.
Thank you.
Okay. Okay, so let's resume the class. We saw just the two transducers that could be used to measure the force and pressure just by taking into account of the strain gauge properties and the Wheatstone bridge, of course. Now, let's change the topic, okay, and let's refer to the strain measurement, okay? So just for a basic background on the strain measurement. Let's refer to the domain. Okay, and this 2D domain is characterized by a point in a XY reference frame like this, for example. Okay, and this reference frame is very useful to define the position of whatever point A. Okay, and the connection between the point A and, for example, the origin of this reference frame is characterized by a length L. Okay, point A, by the way, is having a X coordinate system, an X coordinate and a Y coordinate in the reference coordinate system. Okay, now let's see what happens when we are referring to a strain measurement. So what I've just draw is a simple sketch of a position, a point in your elastic domain, 2D elastic domain, that is having a strain. Let's assume that by using a magnifying zoom, we are considering just a strain in the X direction. So point A will move to a different point. Let me call that A prime, okay? A prime, like this. And the motion, the kinematic of this point is that from A, in order to get the point A prime, we are assuming that the elastic domain is changing its shape so that A is going to A prime following the dashed green line that I just drawn. Because of that, what we are having, once again, we are considering that with a magnifying lens, okay, lens. So this is the change delta of the coordinate x, okay? It is a displacement in the x dimension. Of course, the original position is given you by the x coordinate. Now, because of this, we can also think that the length of the connection line between the origin and A is also changing. Okay, so what we can say is that because of this strain, also the line, the straight line, is also having a change of length that I can tell that is equal to delta L. Let me focus this. Okay, delta L. Of course, we are having this 90-degree angle of that triangle over there, and the angle here is the angle alpha. Okay, so now let's figure out for a while that your strain gauge is bonded to the structure, okay, in a position so that its natural measuring direction is just the one of the angle alpha, and is bonded so that the reference length is L. So let's assume that your strain gauge is somewhere placed like this, okay? Okay. So the question is, what is the strain that the strain gauge is sensing when there is a strain in the x direction? So what we can say is that the strain in the, let me call that alpha direction, that is the natural measuring direction for the strain gauge, that is characterized by an orientation angle of alpha with respect to the reference frame, is by definition given by the ratio of the change of length, delta L, with respect to the basic length, L. Okay? From geometry, what we can say is that the x coordinate is given you by L cosine alpha, and the change of length is given you by the change of the x coordinate because of strain times cosine alpha as well, always from this picture, as you can see. Now, how about the strain in the alpha direction? What we can say is that the epsilon alpha is equal to delta x over x cosine alpha times cosine alpha once again. Okay? Just consider the previous equation that I gave you. But delta x over x is just the strain in the x direction. So the strain in the alpha direction is related to the strain in the x direction through this equation. Okay. So we can say is the epsilon alpha is equal to epsilon x cosine square alpha. Now we can repeat the same approach here, but now considering a strain in the y direction only. So instead of x, just y direction. So what we can say is that if there exists a strain in the y direction, so that the point is moving from the point A to the point A double prime. A double prime now is this point, for example, that is analogous to what we already had. Okay. Remember, A double prime is parallel to the y-axis. Then we can prove that your strain in that alpha direction is equal to epsilon y times the sine square of your angle alpha. And just to remind you, the epsilon y by definition is just the increment in the y direction of the coordinate with respect to the initial reference frame. Okay. So we can put the things together now just by adding the third effect, that is the shear strain. Okay. Once again, if there is a shear strain gamma, epsilon xy, then what we got is this strain that is seen by your strain gauge, that is the strain the direction alpha, is equal to by epsilon xy, your strain gauge definition, sine alpha cosine alpha. Okay, and that is the third equation that we got. 1, 2, and the third one. Okay. So, because we are considering the different and separated effect of having the strain in the x direction, in the y direction, and the shear, because these strains are all small quantities, we can think that if there is a general strain field in that point, then the overall strain is the summation of everything. So what we can say is that the strain in that point in the direction alpha is given you by epsilon x cosine square alpha plus epsilon y sine square alpha plus the shear strain sine alpha cosine alpha. Okay. Just a side remark. Okay, we can have this equation from geometrical consideration as those that we start having looking at this picture. Okay, but also we can get the same information, the same equation, if we consider this strain tensor. Okay, so if we got the strain tensor, for example, if we define D as the strain tensor that is in a 2D domain, a tensor whose components are epsilon x, epsilon xy alpha half, epsilon xy half, and epsilon y, then we can have the same information just by evaluating the strain in the n direction, like the one that is given. Okay, this is the inner product between these two vectors. Okay, and n, of course, is the cosine vector having the components cosine alpha and sine alpha. We got the same result as we already have. So epsilon alpha is also equal to this, where n is the cosine vector component alpha in a 2D domain. Now, what's for this discussion? This is just a remark for you. Is this one. Now go back to your picture here. Now, if I am having the strain gauge that is located as I did in this picture, that is, the strain gauge is located with an orientation angle alpha with respect to a given direction x, y. What is the relation between the strain that is measured by the strain gauge and the corresponding strain in whatever reference frame? The answer to that is given me by this equation. These three equations that goes together with this one. So the question now is, let's assume that I am down in the laboratory. I'm taking the strain measurement in one direction with respect to a given reference frame. How can I get this strain in the given reference frame? Or worse, if I got epsilon alpha from the strain gauge measurement, can I get epsilon x, epsilon y, and epsilon xy? Question mark. The relation is there, but as you can see, we need 3 measurements in order to have epsilon x, epsilon y, and epsilon xy. Because we have just one equation, and with respect to the reference frame with 3 unknowns. So, by the way, what we can say in our experimental point of view, we are having that epsilon alpha is a measure quantity epsilon x, epsilon y, epsilon xy are derived from, oh, sorry, from 3 different measurements and the equation this one. Okay. In order to do that, manufacturers introduce the string rosette. Okay, that is a system composed by 3 different strain gauges oriented with different and very well-known angles. Okay, so that they can have what we call the strain rosette. Okay, just for example, we would like to have a strain gauge measurement, the strain measurement at that point. We are having a strain gauge rosette, so that we are having, for example, a string like this, a strain gauge like that, and a strain gauge like that. We can call that strain gauge number 1, strain gauge number 2, strain gauge number 3. If you consider this point, the strain gauge rosette like that is set, for example, in whatever reference frame, for example, this one, X, Y, and O, you perfectly know what are the 3 orientation angles alpha of each strain gauge 1, 2, 3. So you know, for example, alpha 1, alpha 2, and that is alpha 3. Okay, you can enter this equation, 3 equations, 3 unknowns, and then you got the solution in terms of the strain in the whatever XY reference frame. Okay, okay, time is over. I would like to introduce you some more remarks on the strain gauge measurements with the strain gauge rosette. We'll see that on Friday. Questions from home? Question from the class? Here?
No, Professor, thank you. Bye.
Okay. Bye-bye.
Arrivederci.
Arrivederci. Okay. See you on Friday.